Hey Math 1, I've got a new video for you. It's an extension of the order of operations. We talked about sort of like the basics of what those were and how to use them in the context of geometric formulas. All right, we spent 2 days on that. Now what we're going to do is do a little more formal proving of things. Okay? So the first thing I want to do is just go to a problem that doesn't really have a context. It doesn't have like a geometry formula to work through, and just see if we can step by step go through this with like healthy documentation of what happened, what calculation was done. So the first thing I'm going to do is just restate the given. Like we're trying to get to -6 when we do our, addition, subtraction, multiplication, division, exponents, all that stuff. So here's our original statement. Now when you think of the first thing in order of ops as parentheses, you got to go a little bit beyond that understanding. Brackets are basically parentheses that encapsulate or hold in other groups of parentheses. So really the brackets, what's done inside the brackets has to happen first. So our first move on this is probably to say exponents need to be computed. Not probably, definitely. All right, and I also have 1/16 in parentheses. Nothing's really happening with that 1/16, so to avoid any confusion, I'm just going to write it without the parentheses. And it's put side by side with a second group of parentheses, which would just indicate multiplication of 1/16 times whatever 4 squared is. Well, this is 4 times 4, and it gives you 16. So there's our first move. Our first move was basically saying the only thing that happened that was different was that 4 squared is equal to 16. All right, our next move. We can't do this addition yet because the 2 is connected to the brackets using multiplication. Inside here, I've got addition versus multiplication. Multiplication has to come first. So when you think about 1/16 times 16, how do I multiply a fraction times a whole number? Well, you can put that whole number over 1, and then either multiply top by top, bottom by bottom, and then simplify, or just say, hey, the 16 and the 16 diagonally will reduce to 1 over 1. So this would be 1, right? 1 times 1 is 1. 1 times 1 is 1. It's 1 over 1. It's just 1. And my documentation off to the side would be 1/16 times 16 is equal to 1. That's the change I made. This was in the expression. It is now just a 1. Now at this point, the brackets are down to addition. So I just take -1 plus 1, and that should be 0. This is the point at which I would really start to think about, should I even put the brackets in there the second time? Because the brackets are just denoting, all right? They're representing 2 is going to be multiplied by whatever's in there. So I'm just going to erase these brackets and say it's 2 times 0 so that I recognize, hey, this multiplication must happen before this addition. So that's 0. 2 times 0 is 0. And then anything added to 0 is equal to 0. I'm sorry, let me restate that. Anything added to 0 is itself -6. And that's the end of the proof. You might see in other classes a double slash to say, hey, my proof is over. -6 was what we were trying to get to at the beginning. We got there. So here's the deal. in this lesson, if you're able to do these moves, document them over here, just like I did with those arrows, there's only one new thing you got to pick up as far as the skills are concerned. And it's recognizing what move was actually made. So, if I scroll down through this notes document, all right, and I'm actually not going to erase this just yet. I'm going to move back up, okay, so bear with me. Just look at this top version. There are 6 total properties that can be used to justify any step of the order of operations, any order of operations proof. So what I want us to do is go one at a time and see if we can kind of piece together this proof. So what I'm going to do is off to the side maybe just show the moves made over here. And then I think we'll be able to dissect this pretty well. So give me a second. All right. So it might not be a bad idea to just go in the video, and when this had a white background, just do a screenshot and kind of put it off to the side so you can kind of look at it as we're going through this video. And if you don't, that's okay too. Okay, so 6 total properties. Here's the first one. The multiplicative inverse. I abbreviate it as this. It's basically when you multiply 2 reciprocals, so that might be maybe a term that you've heard before but don't remember what it is. They're basically fraction flips. Like 2/5 and 5/2 are reciprocals. 6 and 1/6 are reciprocals. And when you multiply them together, you always get 1. So that's what it means to be a multiplicative inverse of something. It's when you multiply 2 numbers together and you get 1, that means that you're dealing with 2 inverses with one another. So here's my question. If you move over here, did any step happen in which we multiplied 2 multiplicative inverses together and got 1? Well, yeah, that's right here. So my proof that I had here would need just one adjustment. I'd need to say, and I'll just put it in parentheses beside it, I'd say the multiplicative inverse is what justifies that 16 times 1/16 equals 1. Let's check out the next one. The multiplicative identity. So the multiplicative identity, and here's how I abbreviate it, is when you multiply by the identity. All right, basically it's saying the number that gives you a mirror image. So you're getting that number back when you multiply it by 1. So basically, whenever you multiply by 1, you're backing up your reason for that order of operations proof with the multiplicative identity. So 3 times 1 equals 3. You would say, oh yeah, that's true because of the multiplicative identity. If you saw 3 1/3 times 1 equals 3 1/3 in the middle of a proof, you'd say, oh yep, that's multiplicative identity. If you saw -7 times 1 equals -7, the multiplicative identity backs that up. And guess what? When you take 6/5 times 1 and you get 6/5, that too is going to be the multiplicative identity, which backs up that calculation. So let's check out our proof over here. Are there any steps in which you multiplied by 1? No, 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 no. So that property is not incorporated in this proof. It's not represented. So that's okay. You don't have to have every single property, every single proof that you write. let's continue moving forward. All right, the next one is the multiplicative property of 0, abbreviated as MPOZ. This is whenever you multiply by 0. So it's pretty straightforward in terms of the multiplicative property of 0 is when you multiply by 0. And it's basically just establishing something that we all kind of take for granted. It establishes that, indeed, whenever you multiply by 0, you get 0 at the tail end of that. So if this showed up in a proof, here's how you'd back it up. MPOZ. If this showed up in a proof, you document it with MPOZ. If this showed up in a proof, same thing. And you'd be writing the multiplicative property of 0 as the justifying step. So let's go to our proof over here. This would not be the multiplicative property of 0 because I didn't multiply. I took -1 plus 1. Can you guys see that? Yes, you can. I didn't multiply to get 0, so it's not the multiplicative property of 0. This one definitely is. All right, I think that one's probably the easiest one to remember. All right, the next one is additive inverse, abbreviated addinv. This is when you add or subtract and come up with 0. So basically, the only way to get 0 through addition or subtraction is by adding the inverse or adding the opposite. So yeah, it makes sense why we name it that. So some examples of additive inverse would be if you saw 3 plus -3 equals 0. That's additive. Sorry, I'm having trouble saying this one. If it's 3 plus -3 equals 0, the additive inverse would be our justifying property. It doesn't have to be plus and negative either. If you see 4 minus 4 equals 0, that's the same thing. If you see a negative plus a positive and you get 0, still additive inverse. And then, yeah, fractions can be additive inverses of one another too. So if we roll on over to our previous proof, it's pretty clear that this one has sort of like that, it shares that consistency with specifically this one right here. I mean, it looks identical to it. We just swapped out the 2's for 1's. Yeah? Both of them are additive inverse. All right, we're down to 2 properties. Additive identity. This sort of establishes another property regarding 0. It says that whenever you add 0 to another number, you get the mirror image back. So you should use additive identity whenever it's something like 3 plus 0 equals 3. Or, I mean, it could be 0 could be the starting point, and it's like subtracting 4. If you get the number -4 back, that's using the additive identity. So, just because I'm running out of time a little bit here, I'm not going to rewrite additive identity 4 times. But when you check out this proof, -6 plus 0 equals -6. The justifying property is additive identity. Right? So you're automatically looking at these two and thinking, oh man, am I gonna mix additive inverse and identity up? The answer is maybe, but if you study on it, I think you'll see the difference pretty clearly. Last property. This is kind of like the discard pile, right? It's like substitution property. If it doesn't share any of those special properties, it's substitution. So we're talking like regular calculations. 3 plus 7 equals 10. 5 times 6 equals 30. If you're dividing and you have to convert it into a fraction and reduce, that would be substitution as well. Turning a mixed number into a fraction, squaring a number, So when you look at our first proof, this number would be the substitution property.